Thanks so much. So yeah, good afternoon, everybody, and thanks so much for having me. I definitely appreciate being tracked down to give this talk. I know I've been a little out of touch lately, so I'm really glad to be here. As was mentioned, my name is Gaston. I'm currently Chief Computational Scientist at Idaho National Laboratory, and I also serve as Deputy Director for the DOE NEAMS program. And it was pretty tough to choose a topic to talk about today. And seeing everybody's talks today, I was like, oh, I really want to talk about that topic. I really want to talk about that topic. So I really appreciate all the talks so far today. No problem. But what I decided to do is basically give an update to a talk that I gave to this group 8 years ago at the 20 Years of PETSc conference, where I talked about this idea called application composition. And at the time, it was a fairly new idea that we were kind of kicking around. And I figured, why not? Let's give an 8-year update to see how that went. How did it work out? Okay. So questions I'm going to answer today, first of all, just a little bit of background. What is MOOS, which is the main multiphysics library that we develop at Idaho National Laboratory? What is application composition anyway? How is it being used? How have we been using it? I'll give 4 use cases to show how we're applying it. And then how do we keep it working? Which, you know, the preceding talk did a really good job of talking about all the difficulties of keeping these ecosystems running. And then finally, just a little bit of what next and looking at the future. So first, just a little bit of background on MOOS in case you haven't heard about it. The whole idea behind MOOS is to accelerate the development of high-fidelity modeling and simulation tools. It got started in 2008, so if you do the math on that, I've been working on it for 15 years, which is a long time for me. It's all fully PETSc-based, so we use PETSc both for linear solvers, nonlinear solvers, and preconditioners, and always have. And the idea behind MOOS is to make multiscale multiphysics accessible. In particular, we've heard a couple of times today that domain scientists are spending an awful lot amount of time writing software. And we hope that with MOOS, we can help domain scientists do more science than computer science. It's a complete platform. So it started out as just a C++ finite element framework, but these days it's kind of an end-to-end solution that provides everything from build system to documentation, testing platform, the C++ finite element framework, and then a huge bag of reusable physics components that you can use as well. So it really tries to help you get up and running and develop a new high-fidelity ModSim tool. It's all fully open source, so you can check it out at moosframework.org. We try to do everything as open as we can. And it's massively parallel, always has been MPI and threading from the beginning. It's extremely flexible, as hopefully you'll see through this talk. And it conforms to the NQA1 software quality standards, which are the software quality standards required by the federal government for creating nuclear safety software, because that's primarily what we're doing with it at Idaho National Lab. So just a little bit more about what you get with MOOS. One of the things I really wanted to point out is this huge set of physics modules that you get when you're using MOOS. And these are canned sets of physics that you can just pick up and use. So from day one, you start a new MOOS-based application. You want to solve some new engineering problem. You can make a new MOOS-based application and just turn on these physics and have them immediately. So you can turn on heat conduction, solid mechanics, Navier-Stokes, compressible Navier-Stokes, incompressible Navier-Stokes, whatever you're interested in. And then you already have that physics capability from day one of starting your application. Then you sprinkle in a little bit of your own physics, boundary conditions, material properties, et cetera, into our plug-in system and specialize things for the particular engineering problem you're trying to solve. So this is a great capability to have this repository of physics. These are all open source, all community developed for the most part. And this continues to grow. One that I want to point out over here is stochastic tools. I'll talk about that later on. But this is our primary machine learning AI capability that's in MOOS. To give you an idea of some of the things we can do with MOOS, this is just a sample of MOOS-based applications. So the ones on the left are INL-developed, nuclear-related, or primarily INL-developed, nuclear-related applications. As you can see, we kind of like animals from Northwest US, bison, grizzly, pronghorn, marmot, sockeye. You got to have some naming scheme, right? But you can see they simulate different parts of a nuclear reactor. So nuclear fuel, the pressure vessel, material evolution, CFD, heat pipes, and the neutron transport itself in Griffin. And then over on the right, I'm showing just a selection of 4 applications that I got out of the literature that are using MOOS for bio-inspired vascular networks, solid-state electrolytes, earthquake, I guess I'm not supposed to say prediction, people don't like that word, earthquake forecasting, I suppose. It's not my area, but I've been called out on that before. So just to show you kind of the breadth of things that we can do with MOOS. Now, what I'm going to talk about today is that we've developed all these different nuclear engineering applications that simulate different parts of a nuclear reactor. But what we really want to do is combine them together to have a full multiphysics, multiscale simulation of new reactor concepts. And that's where we get into this idea of application composition. How do you actually take these things and combine them in order to do these complex multiphysics, multiscale simulations? So that brings us back to this rewind back to 8 years ago in the 20 Years of PETSc conference, where I started with this slide right here, simplifying multiphysics through application composition. And I went through some of the basics of this idea, where what I wanted to do was enable groups of people all around the world to develop applications completely independent of each other. But because they developed them in the same way and using the same framework, you can instantly combine them together to do larger, more complex multiphysics, right? That was kind of the idea. And in the intervening 8 years, we've had a lot of success with this. So we have the NEAMS program that I'll talk about in a moment, where this idea is completely underpinning advanced reactor simulation. The Nuclear Regulatory Commission is using this idea and MOOS-based simulation for evaluating all licensing activity for advanced reactors. The UK Atomic Energy Authority is developing a suite of fusion tools using this idea. And then finally, one from here at Argonne National Laboratory, the Cardinal application, which is doing exascale fission and fusion applications. So I'll kind of walk through each of these 4 use cases and show you how they're being applied. But just a little bit more on the idea first. So this was the original animation that I showed 8 years ago, and it turns out I've showed it about 100 times since then. You know, slides have a really great way of, you know, the more time you spend on a slide, the more times you have to show it, right? So I'm going to show it one more time. But the idea here is that if you're trying to make a new simulation tool, in this case we want to simulate nuclear fuel, what are the things that you would need in a simulation tool? So you'd need all those physics at the top, you'd need chemistry, solid mechanics, you'd need a lot of numerical support like parallelism, physics coupling, how to assemble matrices, vectors, etc. How to evaluate finite element shape functions, do time integration, solvers, and even all the way down to message passing. And if you were to sit down, 30 years ago or so and try to develop this application, you would do all of these things, right? But the reason that we're here is because we've learned in the intervening time that the development of numerical libraries is a good idea. And reusing other people's work is a good idea. So to get this kicked off, obviously one of the first libraries that was made was MPI for message passing, as we already mentioned today. And then we realized that we can take solvers and actually make libraries out of them. And we got PETSc, BLAS, LPAC, not all at the same time, but eventually, right? And then the next group of things that we were able to libraryize was finite element infrastructure. So things like reading and writing meshes, finite element shape functions, quadrature, et cetera. There's a lot of libraries that do this today. libmesh is the one that MOOS has used since the beginning. Then on top of that, what we realized is that for multiscale, multiphysics, nonlinear solving, there were a lot of things in common, and that's why we made MOOS, so that we could basically package up all these things that we were doing over and over again for different applications and just do it once. And then on top of that, we said, wait a minute, everybody keeps implementing the same physics over and over, even using MOOS, so let's not do that. Let's create the physics modules in MOOS and try to share those physics capabilities, which has really worked out well. And so finally what you end up with is kind of what's really special just to your application, right? As a scientist or an engineer, these are the things that you know about that you want to study, right? In this case, fission, heating, boundary conditions, and material properties specific to this particular problem, okay? And so using Moose, you can create a new Moose-based application, code these things up, and have a massively parallel multiphysics simulation of nuclear fuel. And at INL, we call that application Bison. Okay, it simulates nuclear fuel. And we've created, as I showed just a moment ago, lots of other applications, including Relapse 7 and Rattlesnake, which is now called Griffin. But as I mentioned just a minute ago, we didn't want to stop there. What we really want to do is tie these applications together. We want to treat these physics applications that were created by completely different groups of people as libraries and create an even larger simulation that includes all of that capability. And so what does that look like? Well, here, 8 years ago, I called it Mammoth. I really love that part. I did this in Keynote. It was great. Mammoth isn't alive today. That's where you get the drums. But there are other applications in the Moose ecosystem that are doing this today, and I'll talk about some of them here. So the idea is have different development groups create their own applications, but all using the same foundation. And then because they're using that same foundation, we can instantly tie those capabilities together in order to do things like a full nuclear reactor simulation. All right, so how does that work? Uh-oh, we're missing some coloring here. So the first capability in Moose that enables this is something called multi-apps. And what multi-apps does, and you should be able to see it in the tree over here, but it's kind of been blanked out here on the transfer, but it allows you to create a hierarchy of Moose-based solves, all in memory, all spread out in parallel, all executing at the same time, all right? And that multi-app, we really mean it. We've instantiated thousands of Moose-based simulations, all simultaneously, all running on the cluster, all communicating to each other, okay? And this is what allows us to run multiple teams' efforts simultaneously. By the way, non-Moose-based applications, if you didn't make it with Moose, we have a wrapping capability. So you can take an external, what we call an external code, wrap it up in a Moose interface, and then it can show up anywhere in this same hierarchy. If you want to think about this hierarchy, you can think of it as a multi-scale solve. Maybe you have your largest scale on top, like a kilometer scale. You have some sort of engineering scale, maybe multiple meters in the middle, and maybe some sort of microstructure simulations that are going on underneath there. And you want to run all these simultaneously. And then using transfers, you can feed that data back and forth through this hierarchy, okay? And all this happens in parallel, in memory, using MPI for all the communication. And there's nothing that you, as a user of Moose, have to write to enable this. You don't even have to modify your code at all in order for it to participate in a multi-app solve like this. Okay, so that's the idea. We use multi-apps and transfers, and we want to tie together multiple Moose-based applications and go after these complex simulations. So how's this being applied? Well, I mentioned the NEAMS program earlier. NEAMS is the Nuclear Energy Advanced Modeling and Simulation Program. It's the primary program in the DOE NE for modeling and simulation of nuclear reactors. And within the NEAMS program, there's kind of two elements. There's kind of the light water reactor simulation side and kind of the advanced reactor simulation side. On the advanced reactor side, we're leveraging Moose and this idea of using multi-apps and transfers for simulating advanced reactors. And the reason why we're doing this is because within NEAMS, there are so many different types of reactors and different scenarios to be able to simulate that trying to create one simulation tool that has all of that capability in it is completely intractable, okay? We've got molten salt reactors, we've got high temperature gas reactors, FHRs, I'll go through a huge list later. But we have all these different types of reactors, and then we need to look at things like design basis accidents, we need to look at what's happening to material composition, et cetera. And so what we need is this flexibility to be able to have all these different pieces and trade them in and out in order to simulate different types of reactors in different scenarios. So for instance, here we're looking at a molten salt reactor, and we have all these different codes to choose from. And if we want to do a design basis accident, we can take Griffin, which is our neutron transport application, combine it with Pronghorn, which is our coarse mesh CFD capability, and SAM, which is developed here at Argonne National Lab as our systems analysis code. We combine these three codes using multi-absent transfers without having to write any code to do it, and do a simulation of a design basis accident, something that you would need to do for licensing a new reactor. But then if we want to look at something different, we want to look at isotope transport or equilibrium concentration calculations, we can bring in another Moose-based code from Oak Ridge National Lab called MOL, which is doing that. Oops. Again, we're getting some transfer issues here, but if we wanted to do salt property evaluation, we could bring in the phase field module of Moose and look at things like corrosion, et cetera, inside the reactor. Haha. Those are not supposed to be up there, all good. And then finally, if we wanted to look at uncertainty analysis, we can use this stochastic tools module that I mentioned earlier to be able to run many, many perturbations of this system. Okay, and I'll get more into that later. And, oh, there's one more. And if we wanted to do some high fidelity correlation development, we can bring in a non-Moose-based code like NECRS that we've been able to wrap in the Moose interfaces and have it serve as our high fidelity CFD capability coupled to neutronics here. All right, so what that gives you is this ecosystem of different tools that we can mix and match in order to go after different reactor types and different scenarios. This is what that looks like pictorially. I know it's incredibly complicated looking, but at the top you have Moose. Underneath that you have all the physics modules that are in Moose. Underneath that you have all the Moose-based applications. Every single one of those kind of red-ish boxes there is developed by a different team of people, okay? But they're all reusing those physics modules, and they're all reusing the capability from Moose. And then we have non-Moose-based applications, or Moose-wrapped applications. Those are the pink ones here. And we have NECRS and OpenMC, for instance. And then we have Trace and FAST, which are Nuclear Regulatory Commission codes. And finally, at the yellow level down here on the bottom, that gets to what we're talking about today, which is combining multiple applications together. So we have codes like Blue Crab, which I'll talk about here in a moment, Direwolf, which is a heat pipe simulation tool. It combines multiple Moose-based codes, and Cardinal, which you'll learn about again here in a moment. So just by using this hierarchy, we can get a ton of code reuse out of the system. Okay, these next few slides I'm not going to go through in detail. The purpose here is to show you that this isn't just an idea that I'm offering up. This is something we're doing every single day, okay? And so here we have sodium fast reactor use cases. And what I want to point out is the different codes that are used. So if you look over here on the right for the VTR simulation, it's using Griffin, Bison, and SAM. And if you look down here at the bottom at the ABTR simulation, it's using Griffin and SAM. And so this is showing how we can trade things in and out. For high temperature gas reactors, we can use thermal hydraulics coupled to heat conduction, coupled to fluid flow with Pronghorn. FHRs, we use Griffin coupled to Pronghorn and SAM, Griffin and Pronghorn, and again, we just use these tools over and over to go after different types of simulations and completely different reactor designs. Okay? Doing this any other way would be completely intractable. If we were to sit down with the limited budget of NEAMS and try to create a full simulation tool for each one of these types of reactors all by itself, a bespoke simulation tool, we would have never gotten there. So the only way that we're able to do to be successful in the program is by using this capability. The last simulation from NEAMS I want to show you is this AGR Trizo compact modeling, where we're studying a graphite compact with 4,000 Trizo particles embedded in it. Each one of those particles is individually simulated by a multi-app. So this is instantiating 4,000 fuel performance calculations embedded inside of a graphite compact, and doing doing thermomechanics between it effectively, along with neutron heating. Okay, so that was NEAMS. So how's the Nuclear Regulatory Commission using this same idea? Well, again, this is one of their slides, actually, and you can see that Moose is kind of at the center here, and there's a few of those Moose-based applications that I've mentioned a few times there. But also over here on the left, we have NRC codes themselves, scale, parks, trace, and fast. And what we've done is we've been able to wrap those up in the Moose interfaces so that the NRC can choose to use either Moose-based applications or their own applications and couple them together in whatever way they need in order to look at licensing of advanced reactors, okay? And in fact, one of the internal projects at the NRC was to couple trace and fast, and they had done this, I don't know, 10, 15 years ago or something like that, but it never really worked all that well. And we were able to do it with Moose, just using Moose to couple their own codes together because of the way the system works. So just having them be able to use their own codes together was also a win. I mentioned the UK AEA. They're developing this suite of fusion-based tools. So, this suite of fusion tools based on Moose. Aurora, Apollo, Proteus, and Phaethon to simulate different parts of a fusion system effectively, including blanket calculations, which I'm showing over here on the right with tritium production. And you can see here they're combining Moose along with other tools, including OpenMC, DAGMC, MFEM, ASCOT5, in order to simulate different pieces. So they're using both native Moose physics and external applications together in order to simulate each of these pieces of a fusion reactor. And my final example here is Cardinal, which is this exascale fission and fusion simulation capability developed at Argonne National Lab by April Novak. And it's effectively Moose plus OpenMC, which is a Monte Carlo neutronics capability, and NECRS, which is a high-fidelity CFD tool. And it's really a showcase for coupling together non-Moose-based applications. So they've been able to simulate a wide range of both fission and fusion systems using these codes and run it up towards exascale calculations using 27,000 GPUs on Summit to simulate a full pebble bed reactor and every single pebble in that reactor, 350,000 pebbles. All the flow through those pebbles, all the heat conduction, and solid mechanics for each pebble, and the neutronics for the whole system as well, all simulated simultaneously, okay? So with Moose, you can really go to really massive, massive scales. All right, so that's what I have. That's how well that idea worked out from 8 years ago. But once we have all these codes working together, how do we keep them working? And this is definitely a problem, as was hinted at in the previous talk. So I mentioned that Moose and several of the Moose-based applications follow an NQA1 development process. It's a very rigorous development process. It requires a lot of documentation, a lot of handoffs, a lot of sign-offs, et cetera, all right? And that's pretty incongruous with how we want to develop the software. If you just look down here at the last 30 days of Moose, it's a pretty lively project. We've had 83 pull requests merged by 27 different authors, and adding 50,000 new lines of code just in the last 30 days, all right? So there's a lot going on here. And we can't sit around and sign off on paper and run tests manually, et cetera, all right? So to keep all this working together, we've developed another open source piece of software called Civit, which is a massively parallel continuous integration capability. Now, we did this many years ago before GitLab and GitHub had their own continuous integration capabilities, and back whenever Jenkins was kind of the best thing running and was not a great thing running. But over the years, GitLab and GitHub continue to kind of catch up to where we are, but they're still not there as far as capability. But we hope someday that we don't have to continue to develop Civit, by the way. It's not something that we're doing because we really enjoy it. It's something that we're doing because we have to. As you can see, there's been 200 code contributors to Moose with 45,000 commits. In order to keep all that working, we run over 60 million tests per week across a dedicated testing cluster with 3,000 cores in it that is spinning constantly. And you can see up here on the right kind of a schematic of how all the automated testing and verification goes. And we do both continuous integration and continuous delivery. So again, building on the previous talk is very, very similar as far as needing to create packages that developers use and create packages that end users ultimately use. And we actually use Conda for actually doing the package distribution itself. The other way that we keep all this working is, so there's the code itself as far as keeping everything compiling, keeping everything running together, but then how do you keep all these models that everybody is creating working? So we've got these models that are using 3, 4, 5 different Moose-based applications. Each one of those applications is under constant development, plus the framework being under constant development. How do your users know that something has updated or that their model is still working? And to do that, we're using something called the virtual testbed, which is another open source capability of, it's a repository of models using these Moose-based applications. I'm running out of time, so I'll just show you this image here. This, once again, underscores the complexity of what we're trying to do. These are some of the models on the virtual testbed and the combinations of codes that go with them. To get access to those codes, use the NCRC at INL. And I do want to talk about next for just half a second. What's coming next? What do we do? Well, I mentioned the Stochastic Tools module a couple of times. I'm not going to go through the detail here, but if you're interested in combining together machine learning with simulation, you should definitely check out our papers on the Stochastic Tools module. This is basically taking stochastic sampling and putting it on the inside of an application instead of doing it from the outside. And that gives us a lot of advantages. We have an in-memory backup and restore capability in Moose, where we can take an in-memory snapshot of any application and then restore it back to that state at some later time. And we're able to use that in the Stochastic Tools capability to do really, really fast sampling by having an application stay resident in memory and just resetting it back to its original state with new inputs and then running it again. We can do millions of samples on some of these fast-running calculations in order to do things like develop surrogate models, do Bayesian modeling, create proper orthogonal decomposition surrogate models, et cetera. All right, final slide. Evolution here. Well, we're going to be working on more transfers. That's always the case. More flexible execution in iteration schemes. Dynamic loading is a new capability that's there now, meaning you don't even have to compile these Moose-based applications together. You can just say at runtime, I want to go pick up that application, and it loads it into memory, and you can, and you're off and running. GPU capability is certainly coming to Moose. We're starting to put it into different parts. And then the big news, though, for this hot off the presses is that Moose is going to be moving to MFEM going forward. So we're going to be transitioning away from libmesh, which has been our finite element library since the beginning, and move over and join forces with the guys from Livermore on MFEM. So. That's what I had today. Thanks for listening. Oh.
How much have you thought about or done with communicating derivative information between your different applications?
Absolutely. So when Moose first started 15 years ago, automatic differentiation wasn't so much of a thing. In the intervening time, we've added automatic differentiation all the way through the framework. And so it's all forward mode. It's fairly simple, template-based automatic differentiation, but it lets us compute derivatives between all the terms on the right-hand side. So we are able to completely create Jacobian matrices and things like that with AD. And that it does help a lot whenever you have different physics coming from different applications and they're being combined together in material models, et cetera, and we need to be able to compute derivatives of those things. So, yeah. Matt.
So I think to stay on schedule, we need to get our next speaker up here. We can have more questions offline. Thanks again to Derek.
Yep. Thank you.